everyone and welcome back. Now in the last video we saw our first application of neural networks to dynamical systems, and it's a simple, straightforward application, black box forecasting. But we saw that if we build in dynamic information, then we can get better predictions. Now what I would like to talk about in this video is a very novel application of neural networks to partial differential equations in particular, called physics-informed neural networks. Now, the sort of naming of this, PINs, physics-informed neural networks, is coming from a 2018 paper that I'll link to in the description. But the ideas behind this go back at least to about the early 2000s. Again, I'll put some of the history of this in the description for you. But this is really coming out of George Karnadakis' group at Brown University. And I want to do it by example. Okay, so in particular, I want to give you a partial differential equation, and let's talk about how we can solve it. Okay, so here it is. I'm going to talk about the heat equation. So if you followed my lecture series on the heat equation, you'll know how to solve this, right? But sometimes, there are partial differential equations that we can't solve explicitly, and we'd like to simulate them. Okay, so let's imagine we couldn't solve this, even if we could. In this case, we have an exact answer. We can always compare with the exact answer. In this case, our space is going to be -1 to 1. And let's imagine we want to step this one time unit into the future. Okay, and of course, because space is bounded, I need to have a boundary condition here. Let's put a boundary condition. We're going to use a Neumann boundary condition. So x is a function of both space and time. At both of the endpoints at plus or minus 1 for all time, the derivative should be 0. If you watched my partial differential equations lecture series, this is what I call the swimming pool conditions, right? No information can be lost at the boundaries here. And of course, this has to hold for all time. And then, of course, we need to know how this thing is initialized as well, x comma 0. And in my case, let's just use a simple mode. Let's use cos of pi x, okay? And this is going to be for all x between -1 and 1. This satisfies the boundary conditions. We don't have to worry about any of these problems here. You can find the exact solution to this thing. In fact, I'll just tell you what the exact solution is. So if you can solve this using separation of variables and sine and cosine series, u of x of t is equal to e to the minus 0.1 pi squared t, and then times cos of pi x. And you can very easily check that this satisfies all three of these conditions. I mean, it's a fun exercise to solve these things. Everybody loves solving partial differential equations, of course. But now I want to sort of think about, okay, I have a problem. Now imagine I don't know the answer to it, but I'd like to simulate this on the computer. Classic problem in numerical analysis, right? This is the whole purpose of a lot of numerical analysis, is solving things like partial differential equations. Now, what PINs comes around and does is it puts the paradigm in the machine learning perspective. And in particular, what it says is, okay, well, I have things like universal function approximation theorems, and they tell me they can I can use a neural network to approximate any function, right? So why not have it approximate the solution to a differential equation? That's a function, right? And all of these modern advances in neural networks to do things like backpropagation, to do automatic differentiation, I can use those to differentiate the neural network itself. So not only can I approximate a function by a neural network, but I can also approximate its derivatives symbolically. And what do I mean by this? Okay, well, here's what PINs sets out to do in the sort of simplest form. It says, build me a neural network that looks like this. Okay, so this is my neural network. Okay, x goes in, t goes in. You give me a point in space, you give me a point in time, you put those things in, and you should give me the solution to the heat equation back. Okay? Now, I don't know what this is, but this is just a big old neural network. And remember, the neural network is filled with all kinds of trainable parameters that when we do the training of this thing, we have to take a gradient with respect to. But then we can think about x and t as being parameters of the neural network, and we can take derivatives of the output of this thing, of the neural network itself, with respect to the inputs, using the same basic processes. Why? Okay, well, remember, a neural network was something like a sigmoid function, wx plus b. All right, this is like the simplest version of a neural network. We were doing all kinds of partial derivatives of this thing with respect to w or with respect to b. But those are just arguments inside of this thing, so why not just take it one further? Take one with respect to x as well. So that means that you not only get the neural network, but you get the derivative of the neural network. And that's exactly how this works. Pins takes derivatives of neural networks. And again, this is done symbolically, right? This is not done at data points. It's done symbolically through backpropagation in the chain rule. So what we can do is we can set up loss functions that try to satisfy 1, 2, and 3. So how do we do that? Well, what we're going to do is we're going to take, so let's call this like the loss function. The loss function is going to have 3 pieces to it. 1 to satisfy each of the 3 conditions. Okay, so I'm going to say the big loss is the loss of the partial differential equation. I'm going to call it L sub u, the PDE loss, so satisfying the PDE, plus the loss of the boundary conditions. I'm going to call it, say, B for boundary, plus the loss of the initial condition. So we'll call that L0 for time 0. Okay? So the question is, what does each piece look like? Well, let's start with LU. Okay? Here's what I'm going to do. I'm going to think of x and t space, right? So u is a function of x and t. I'm going to think of a big grid here. So tx, this is my domain, right? It's a big square domain. And I'm going to pick a whole bunch of points from this domain, okay? So I'm going to pick a bunch of ordered pairs. So, right, just randomly choose a bunch of evaluation points in this domain. So I'm going to think of a set of xi of u, ti of u, and the u is going to match this u up here in a second, which is going to run from 1 to, let's say, some capital J of u. You get to pick these points, which are points in space and time. I'm using open and closed intervals here, sort of loosey-goosey. It doesn't really matter because they're randomly selected points. But essentially here, I'm going to take 1 over 2ju, so normalizing by the number of points you have. Then I'm going to sum over all of these points, j1 to j sub u. And I'm going to look at the neural network loss at each one of these points, okay? So I'm going to use u to represent the neural network, okay? And so that means that if I want to satisfy the PDE, that means that if I take the neural network and I do a partial derivative with respect to the t argument that comes in, and I evaluate this at each of the points, right? This, by the partial differential equation, should be equal to 0.1 times the second partial derivative of the neural network with respect to the other input, x, at all the same points. Now, I want you to be very careful here. So this is mean square error loss. I'm sorry, I'm writing off the edge here. Be very careful. The derivatives are symbolic differentiation, using backpropagation, but then you have to do pointwise evaluation along these points, right? Because matching up these two functions would require an infinite dimensional norm. Okay, then you can do this for LB as well. Now, think about the boundaries here. Here's one boundary. Here's another boundary. So I'm going to pick a whole bunch of points on the boundary as well. So let's do, I'm going to do points like plus or minus 1 and then a bunch of TIs on the boundary. So a bunch of time points along the boundary. And this is going to go from I to j sub b, so some number. And this is going to be in plus or minus 1 on the boundary by the time interval. And I'm going to do the same thing. I'm going to create a loss function that respects what should be happening on the boundary. And on the boundary, I should have that the derivative of the neural network with respect to x at each of the boundary points, so let's say plus or minus 1 and ti and b, that should be 0, right? That should be completely 0 because that's what I want to satisfy right here. And let's do this again. Last one, right? L0, you can probably see how this is going to work. Here's that other boundary. Then I'm going to get a whole bunch of points here, so I'm not going to define what the points are because I think you get the point. But then this is going to be the sum from 1 to, like, let's say j0 of, now what we want to do is satisfy this condition. So that means I want the neural network at these initial points to be equal to, what did I say, cos of pi xi zeros. So again, think about how clever this method is, right? Neural networks can approximate any function, so why don't they approximate solutions to partial differential equations? Backpropagation allows me to do quick symbolic differentiation of neural networks, so why don't I take derivatives with respect to the inputs too? So then I build a loss function that tries to fit each of the, in my case, 3 pieces of my partial differential equation. 1, it should fit the differential equation, right? 2, it should fit the boundary conditions. 3, it should fit the initial conditions. Now, of course, if your partial differential equation comes with more or less information, you would just build your loss function to satisfy each of the pieces of information that you needed to satisfy. But this is the beauty of pins, right? It's kind of obvious almost, right? It's amazing that it wasn't thought of earlier in some sense. But I really want to emphasize the reason it's become so popular recently is because computing power is much better. Massive advances in training of neural networks through stochastic optimization, better algorithms for backpropagation, automatic differentiation have made this publicly accessible in a way. Let's see with an example. Let's take a look at an example of a pin in TensorFlow. Now, in particular, I would like to begin by giving thanks to Jan Blechschmidt. I apologize if I mispronounced that. Jan actually wrote most of the basis of this code, and I've used or reused it with their permission. Okay, so again, we're going to use TensorFlow and NumPy. Here, what we're going to do is we're going to define our initial condition. This is my cos of pi x, so I want to be able to put numbers into this thing, so I just made it a definition. You can go in, you can put different initial conditions, cosine plus cos squared or something like that, or have a little bit of fun here, do all kinds of funky initial conditions. Just make sure you respect those boundary conditions because, again, you got to think about PDE theory here. You got to think about cosine and sine functions and expansions for these solutions. In this case, my boundary conditions are just going to be 0. But of course, you could have forced boundary conditions as well. These could be forced in time. You can do all kinds of funky stuff here and have tons of fun. And then here I have my PDE residual. So here's the time derivative minus the viscosity value. This is what I had set to 0.1 in the demonstrations that were here on the board, and then then times the second partial in space. Here what I'm going to use is 500 points at the initial condition, so that's at time 0. I'm going to use 1,000 points on the x boundaries, so at plus or minus 1, and I'm going to use 10,000 points inside the domain. R here stands for residual, but I could have just as well used n sub u for the PDE solution here. Now here's the beauty. I get to choose how many points I use, right? And we know that neural networks do better when they have more data. So of course, use as much as you can that you can, try and, as long as the problem still remains manageable. But of course, I want to use lots of points for the evaluation, because you could think about this as a sort of interpolation problem, right? The more points on the solution you have pinned down, the sort of better this solution is going to approximate, or the neural network will approximate the true solution here. So let's take a look. Here what I'm plotting in this next piece is that space-time block. That was the little square that I had down here. You can see space and you can see time here. The red dots represent each one of the sample points that you're going to evaluate the solutions on. Here you can see the 0 boundary conditions, and then here's the cosine. That's that sort of that surface plot that you're seeing, this sort of bird's eye view plot, just showing the high and low points of the cosine function. So now we're going to set this up as a neural network. Here again, I'm going to use 8 layers. Okay, so last video you saw I used 4 layers. Again, these are hyperparameters. You have to go in, you have to really play around with them. And I'm going to use 20 neurons, or width of 20 for each layer. Okay, so you should really think about this neural network as being like long and short, right? So it's extended with a whole bunch of layers, but each layer doesn't have a huge width to it. Okay, and the activation functions I'm going to use here are hyperbolic tangents. These are dense layers as opposed to, say, convolutional layers, which we will not talk about in this lecture series. And here I'm going to, you can see that I'm setting up these partial derivatives, this tape dot gradient. These are taking these gradients, using backpropagation, the neural network output u with respect to the input t. Similarly, to get the first derivative in x, I have this gradient right here, and then I've got to do it again in order to get the second derivative, okay? And then everything else that you're looking at in this section here is really just building up those loss functions, enforcing each of the residuals, and evaluating them at the points. So here's the boundary points, TB and XB, for example. Here now we're just putting up the gradient. We're putting this together for the gradient of the loss function, and we're going to initialize the model. Again, we're going to use atom optimization here, and let's take a look. Let's actually train this thing. We're going to do this for 5,000 iterations. In machine learning, this is called an epoch. And again, you can see this thing getting started up. It's printing the loss every 50 epochs here instead of just every epoch. Remember, the solution to this thing is the original cosine with an exponential decay. So really the only thing that happens is the cosine comes down. You can download this, you can run this on your own, have some fun, try with different initial conditions, different boundary conditions, even a different PDE, have a little bit of fun here. Try burgers, for example. But here's what I want to do. I want to show you the solution. So here is what you were just looking at on the previous example. The red is the initial condition. The blue is the exact time 1 state. So if you take the exact solution and put t equal to 1 into it. And what I've done on the right-hand side here is compared the pin solution with the true solution in black dotted. And to plotting accuracy, these things are exactly the same, right? And I've computed the L infinity norm along the sampling points. This is in the book. I believe it's like 10 to the minus 3 or even smaller, right? So for neural networks, that's pretty darn good. So then you might have the question, you say, okay, well, I trained up a neural network. It gets me to time 1, but of course, these are dynamical systems. I want to walk through time. I want to keep forecasting this thing. Can I use that same that same neural network to predict what the solution would look like at t equal to 2, for example, or even t equal to 1/2 or t equal to 10? And the answer to this is very much no, okay? So this is an example of what would happen, or what had happened to me. This is at time 2. Black is the exact solution. The blue here is what the PIN, the physics-informed neural network, is predicting this solution will be. You can see that these things are wildly different. In particular, the PIN does not even satisfy the boundary conditions anymore. And this should kind of make sense, right? The PIN was only trained on the square, -1 to 1 in x, 0 to 1 in t. It knows nothing about what happens outside of that box, right? So if we try to go all the way up to t is equal to 2, the PIN never was trained there. It has no information. It has nothing to it doesn't even know it needs to satisfy the differential equation out there, let alone the boundary conditions. This is a slight drawback of physics-informed neural networks, right? Is that they don't learn causality in the way that time-stepping methods do, Runge-Kutta methods, or upwind schemes, or all of these things that we learn about in dynamical system, or in numerical analysis for dynamical systems. So I want you to appreciate the beauty and the simplicity of PINs, right? Using neural networks to simulate and solve partial differential equations, but also recognize their downsides, right? And one downside is that, outside of the training region, these things are completely useless, as you can see with this picture right here. Now, when we come back in the next video, we're gonna actually take a look at an application of PINs for model identification. So kind of doing Cindy, but with PINs. And in what we get here is really sort of discovering partial differential equations from data. So I'll see you all in the next video, everybody.